What if the universe has secrets that resist being uncovered? Not because they are hidden, but because they exist beyond the limits of human intuition. For centuries, we believed reality was built from solid matter, fixed space, and flowing time. Yet modern physics tells us something far more unsettling, that beneath everything we see lies a structure so strange, so abstract, that it challenges the very way our minds evolved to understand the world. Perhaps there are truths written into the fabric of the cosmos that we were never meant to discover, yet here we are, standing at the edge of them. As we push deeper into the foundations of reality, an unsettling pattern begins to emerge. The universe, when examined closely, does not behave in ways that feel natural to the human mind. The solid world we experience every day, chairs, walls, planets, stars, begins to dissolve under scrutiny. Atoms are mostly empty space. Particles are not really particles at all, but excitations of invisible fields. Even those fields are described not by tangible qualities, but by abstract mathematics. The more accurately we measure reality, the less it resembles the world our senses evolved to perceive. This should not surprise us. Human intuition is a biological tool shaped by survival on the African savanna. Our brains are optimized to track predators, judge distances, recognize faces, and predict simple motion. They were never designed to comprehend subatomic probabilities, curved space-time, or dimensions beyond the familiar three. Yet modern science insists on dragging us far beyond this comfort zone. Each breakthrough pulls another layer of reality away, revealing structures so strange that even physicists struggle to describe them without resorting to equations. Consider how deeply misleading our senses are. We experience time as a steady flow, yet physics shows that time bends, stretches, and slows depending on speed and gravity. We experience space as rigid and fixed, yet it can warp and ripple. We experience objects as solid, yet solidity is nothing more than electromagnetic repulsion between clouds of probability. Reality, at its core, does not operate on the rules our intuition expects. This gap between perception and truth is not a failure of science. It is evidence that we are trespassing into realms never meant for biological intuition. Each generation of physics feels this shock. Newton's universe made sense. Objects moved predictably, causes led to effects. But Einstein shattered that simplicity, revealing a universe where space and time are dynamic, intertwined, and observer-dependent. Then quantum mechanics went further, dismantling causality itself and replacing it with uncertainty. At the quantum level, the universe behaves in ways that appear almost hostile to human logic. Particles exist in multiple states at once. Outcomes cannot be predicted with certainty, only with probability. Measurement does not merely observe reality, it helps create it. These are not philosophical interpretations imposed on physics. They are experimental facts confirmed again and again. The universe, at its most fundamental level, refuses to behave like anything we evolved to understand. Probability replaces certainty. This is one of the most disturbing ideas ever discovered. In everyday life, things happen for reasons. Drop a glass, it falls. Strike a match, it lights. But in quantum mechanics, nature does not commit to outcomes until the very last moment. Events unfold as a spread of possibilities, collapsing into a single result only when interaction occurs. Reality, it seems, is not a fixed script, but a constantly updated draft. This challenges something deeply ingrained in us, the idea that the universe has a definite state at all times. Instead, quantum theory suggests that reality exists as a haze of potential until forced into specificity. This is not mysticism. It is the foundation of technologies we already use, from lasers to semiconductors to quantum clocks. Our entire modern world runs on principles that defy common sense. Even more unsettling is that the mathematics describing this probabilistic universe works perfectly. The equations are astonishingly precise. They predict experimental results to many decimal places. The problem is not that the theory is vague. The problem is that reality itself is vague. The universe behaves like a casino, governed by odds rather than certainty. yet structured by laws so exact that they leave no room for error. This raises a disturbing question. If the universe is fundamentally probabilistic, then determinism, the idea that the future is fixed by the past, may be an illusion. On the smallest scales, nature seems to roll dice. This was deeply troubling even to the founders of quantum theory. The discomfort is not aesthetic. It cuts to the core of how we understand cause and effect. Yet the universe does not care about our discomfort. It operates according to its own rules, whether we find them intuitive or not. Each experiment pushes this truth further. Particles appear to influence each other instantly across vast distances. Information seems more fundamental than matter. Reality behaves less like a machine and more like a complex mathematical structure unfolding according to rules we barely grasp. The deeper lesson here is not that reality is unknowable, but that understanding requires abandoning intuition. Physics progresses not by trusting what feels right, but by following evidence, wherever it leads, even into conceptual territory that feels alien. We are uncovering a universe that is colder, stranger, and far more abstract than anything imagined before. And perhaps this is where the unsettling thought takes root. What if the universe was never designed to be understood intuitively? What if our success in uncovering these truths is an accident of mathematics rather than destiny? We are using tools, logic, equations, experiments that evolution never prepared us for, and somehow they work. They open doors into realms that feel almost forbidden, revealing a cosmos that does not bend to human expectations. As we continue to peel back the layers, one thing becomes clear. The universe is under no obligation to make sense to us, and yet, piece by piece, it allows itself to be uncovered not through intuition, but through relentless questioning and mathematical insight. Each discovery brings clarity, but also a growing realization that reality, in its deepest form, may be something the human mind was never meant to feel comfortable with, only capable of describing. As physics pushes beyond particles and forces, it arrives at a startling possibility. Space and time themselves may not be fundamental ingredients of reality. They may be secondary, emergent features like temperature rising from the motion of atoms. This idea runs directly against everything we experience. Space feels like the stage on which events unfold, and time feels like the river carrying us forward. Yet when equations probe the smallest scales and the highest energies, those familiar notions begin to unravel. Einstein already cracked the first layer of this illusion. Space and time were no longer separate entities, but fused into a single fabric, flexible and dynamic. Gravity was not a force acting across distance, it was the bending of space-time itself. Massive objects told space-time how to curve, and space-time told matter how to move. This elegant picture explained everything from the orbit of Mercury to the expansion of the universe. But even this triumph hinted at something deeper. If space-time can bend, stretch, and ripple, perhaps it is not fundamental after all. When quantum mechanics enters the picture, the cracks widen. At extremely small scales, space-time becomes restless. Quantum fluctuations jitter violently, producing a froth of microscopic black holes and warped geometry. The smooth fabric Einstein described dissolves into chaos. The equations stop making sense unless space-time itself is treated not as a given, but as something that emerges from a deeper layer of reality. This realization has led physicists toward a radical conclusion. The universe may be built not from space and time, but from information and mathematical relationships. In some theories, space-time arises from networks of quantum entanglement, where connections between particles define geometry itself. Distance becomes a measure of correlation rather than separation. Time becomes an ordering of information rather than a universal flow. If this is true, then asking what happened before the Big Bang may be like asking what is north of the North Pole. The question assumes a framework that no longer applies. Time itself may have crystallized out of a more primitive, timeless structure. The beginning of the universe may not be a moment in time, but the moment time came into existence. This idea feels deeply unsettling because it strips away the backdrop we rely on to make sense of anything. Without space and time as fundamentals, causality itself becomes ambiguous. Events may not happen in a simple before and after sequence. Instead, reality may be governed by relationships encoded in abstract, mathematical structures that do not unfold, but simply exist. This brings us to an even stranger conclusion. As we move deeper, physics becomes less about tangible things and more about equations. Particles are described not by shape or substance, but by mathematical objects called fields. Forces are interactions between symmetries. Reality appears to be written in the language of mathematics, and that language works with an effectiveness that borders on the mysterious. Mathematics does not just describe the universe, it predicts it. Equations written on chalkboards decades ago later reveal particles, waves, and phenomena that experiments eventually confirm. This raises a profound question. Are we discovering the universe, or are we uncovering a mathematical structure that exists independently of us? If the latter is true, then physical reality may be a shadow cast by deeper mathematical truths. This idea feels alien because mathematics is not something we can touch. It has no color, no temperature, no weight, and yet it governs everything. The behavior of galaxies, the decay of atoms, the flow of time itself all obey mathematical rules with astonishing precision. The universe seems less like a machine built from parts and more like an equation solving itself. At this level, physics begins to feel almost inhuman. There are no familiar reference points, no up or down, no before or after, just abstract relationships unfolding according to strict logical necessity. It is here that the unsettling thought returns. Perhaps reality at its deepest level was never meant to be understood intuitively, because it is not built from the kinds of things intuition evolved to grasp. Human minds are comfortable with stories, causes, and sequences. Mathematics offers none of that comfort. It offers consistency, not meaning, structure, not narrative. And yet when we trust it, it leads us unfailingly closer to truth. The universe responds to equations, not metaphors. This creates a strange tension. On one hand, physics is achieving unprecedented clarity. On the other, the reality it reveals feels increasingly distant from human experience. We are learning more than ever, yet feeling less at home in the cosmos. The deeper we go, the less the universe resembles a place, and the more it resembles an idea. And perhaps this is the heart of the discomfort. If space and time are emergent, if reality is fundamentally mathematical, then our everyday experiences, a surface illusion useful, stable, and necessary for survival, but not reflective of the deepest truth. We live inside a simplified interface. While the real machinery of existence operates far beneath our awareness, still we continue. Not because it is comfortable, but because it is compelling. Physics does not ask whether we are ready for these ideas. It simply reveals them, one equation at a time, pulling us toward a view of reality that is colder, stranger, and more abstract than anything our ancestors could have imagined, yet undeniably real. As we follow this trail deeper, another unsettling idea emerges. The universe may not merely contain information, it may actually be made of information. This is not a metaphor. In modern physics, information has a precise meaning, and it behaves like a physical quantity. It can be stored, transferred, compressed, and even lost. Black holes, once thought to destroy information forever, forced physicists to confront this idea head-on. When matter falls into a black hole, everything about it seems erased except mass, charge, and spin. Yet quantum mechanics insists that information can never be destroyed. This contradiction shook the foundations of physics and led to a radical conclusion. Information must be preserved, even if it is scrambled beyond recognition. This realization transformed our understanding of reality. Black holes are no longer just cosmic vacuum cleaners. They are laboratories for the deepest laws of nature. The surface of a black hole, its event horizon, appears to encode all the information about what falls inside it. This led to the holographic principle, one of the most astonishing ideas in modern science. According to this principle, the information describing a volume of space can be stored on its boundary, much like a hologram where a two-dimensional surface encodes a three-dimensional image. In other words, the universe may be like a cosmic hologram where the reality we experience is a projection of information written on a distant surface. This idea is not science fiction. It arises naturally from attempts to unify gravity with quantum mechanics. If space itself is emergent, then it makes sense that the information defining it might live elsewhere on lower dimensional structures. Our three-dimensional world could be a shadow of deeper processes occurring on a two-dimensional boundary far removed from our perception. What we call distance, depth, and volume may simply be convenient illusions arising from how information is organized. Once we accept this, reality becomes profoundly strange. Objects no longer feel like fundamental things. They become patterns of information, stable arrangements in an underlying informational ocean. Even particles, once thought to be indivisible, dissolve into excitations of fields. And those fields themselves may be expressions of something more abstract still. The universe begins to resemble a vast computation, processing information according to precise mathematical rules. This naturally leads to the idea that the laws of physics themselves may evolve. Traditionally, laws are assumed to be timeless and immutable. But if the universe is fundamentally informational, then its rules may emerge, statistically shaped by consistency, stability, and self-organization. Just as temperature emerges from the collective motion of atoms, physical laws may emerge from deeper informational dynamics. What we experience as fixed laws may be frozen accidents of cosmic history, selected because they allow complexity, structure, and observers to exist. This possibility changes how we view our place in the cosmos. We are no longer passive spectators in a pre-written script. Our existence may be intertwined with the very structure of reality. Observers play a crucial role in quantum mechanics, where measurement affects outcomes. If the universe is informational at its core, then observation is not an afterthought. It is part of how reality defines itself. The act of measurement is not just recording information, but participating in its organization. From this perspective, consciousness itself becomes a subject of physics, not mysticism. Consciousness may be a process that extracts meaning from information, creating a coherent narrative from raw data. While physics does not yet explain consciousness, it increasingly recognizes it. And ignoring the observer leaves the theory incomplete. The universe seems to require observers not just to be known, but to be fully defined. This brings us to another disturbing implication. If reality is informational and possibly computational, then it may be possible to simulate entire universes. The same equations that describe our world could, in principle, be implemented in sufficiently powerful computational systems. This raises the uncomfortable question of whether our universe itself could be a simulation. While this idea is speculative, it follows logically from the notion that physical processes are equivalent to information processing. If the laws of physics can be written as algorithms, then reality itself may be algorithmic, even without invoking simulations. The idea reshapes our understanding of existence. The universe no longer feels like a solid structure built from matter and energy alone. It feels like an evolving pattern, a self-consistent flow of information unfolding according to deep mathematical principles. Space, time, matter, and energy become emergent properties, not the foundation. This shift is difficult to accept because it undermines common sense. We are wired to believe that what we see and touch is real in the deepest sense. But physics keeps telling us otherwise. The deeper we go, the more reality slips away from sensory intuition and into abstraction. What remains is not emptiness, but structure so subtle that it can only be grasped through mathematics. And yet, despite how alien this picture is, it works. It explains why black holes behave the way they do, why entropy governs the arrow of time, and why the universe can be so precisely described by equations. Unifies ideas that once seemed incompatible and opens doors to questions that were once unaskable. At this level, discovery feels less like uncovering hidden objects and more like decoding a cosmic message. Each breakthrough peels back another layer of illusion, revealing a universe that is not built the way it appears, but far more elegant and far more strange. As these ideas mature, we are forced to confront an uncomfortable realization: there may be limits not only to what we can observe, but to what we can ever truly understand. Physics has always progressed by extending human intuition through mathematics, but mathematics itself may be pointing toward realities that resist visualization altogether. Higher dimensions, quantum superpositions, and abstract informational spaces are not things the human brain evolved to imagine. Our minds were shaped on the savannah, not in the depths of space-time. Yet the universe is under no obligation to be understandable to us. Advanced theory suggests that reality may contain extra dimensions curled up beyond our perception dimension that influence the behavior of particles and forces without ever revealing themselves directly. These dimensions are not hidden behind a curtain we simply need to pull aside. They exist at scale so small or in configurations so abstract that direct access may forever remain impossible. We infer their existence not by seeing them, but by the mathematical consistency they bring to our theories. In this sense, we are already discovering things we were never meant to see, guided not by intuition, but by logic alone. This marks a turning point in the scientific method. Observation, once the ultimate authority, now shares its throne with inference. We believe in quarks not because we see them, but because without them, the universe would not make sense. We believe in curved space-time because without it, gravity collapses into contradiction. And we entertain the existence of hidden dimensions because without them, our most ambitious theories fall apart. Reality, it seems, is increasingly defined by what must exist, not by what can be directly measured. This leads to a profound tension. On one hand, our theories grow more powerful and predictive. On the other, they drift further away from direct human experience. The universe becomes a place described not by images but by equations. Beauty is no longer visual, it is mathematical. Elegance is measured not by simplicity of appearance but by internal consistency. We may be approaching a stage where understanding means trusting structures we can never intuitively grasp. At the same time, physics hints that reality itself may place barriers in front of us. Quantum uncertainty limits what can be known simultaneously. Cosmic horizons limit what can ever be observed. Even information itself may be constrained by fundamental bounds. These are not technological obstacles waiting to be overcome. They are woven into the fabric of nature. The universe seems to say, up to this point you may know, beyond it you may not. And yet this is not a defeat. It is a revelation about the nature of knowledge. Science was never about achieving absolute certainty. It was about refining better questions. Each limit we encounter reshapes our curiosity rather than extinguishing it. The realization that some truths may remain forever abstract does not diminish their significance. It elevates them. It reminds us that the universe is not a puzzle designed for human satisfaction, but a vast structure governed by its own internal logic. This realization also humbles our sense of importance. We are not central observers standing outside the universe, decoding it from a privileged position. We are patterns within it, subject to the same laws we attempt to uncover. Our brains, our thoughts, and our instruments are all products of the same cosmic processes we study. When we probe the universe is, in a sense, probing itself. Perhaps the most unsettling idea is that some aspects of reality may be fundamentally inaccessible, not because they are hidden, but because knowing them would require cognitive structures we do not possess. Just as a fish cannot comprehend fire, there may be layers of reality that lie beyond the conceptual reach of the human mind. Mathematics allows us to glimpse these layers, but not to inhabit them mentally. And yet, the story does not end in silence or despair. Even if we were never meant to discover certain truths, the act of approaching them reshapes our understanding of everything else. Each breakthrough expands the boundary between the known and the unknowable. Each equation carved into the stone of physics is a testament to how far a curious species can go, armed only with reason and imagination. The universe may not care whether we understand it, but the fact that it is understandable at all, even partially, is extraordinary. From the vibration of strings to the whisper of information on cosmic horizons, reality reveals just enough to inspire awe without surrendering all its secrets. In standing at that edge, confronting ideas that strain our comprehension, we do not diminish ourselves, we define ourselves. As we reach this point, what becomes clear is that the universe is far stranger and more subtle than anything our everyday experience prepares us for. Each layer of reality we peel back reveals not solid ground, but deeper patterns, abstract structures, and hidden rules that govern everything from the smallest particle to the largest galaxy. The more we learn, the more we realize that discovery is not about conquering the universe, but about learning how to listen to what it allows us to hear. Some truths may always remain just beyond our grasp, not because we have failed, but because the universe is richer than any single species' ability to comprehend it fully. Yet this is precisely what makes the journey meaningful. To explore a cosmos that does not bend to our intuition, to pursue knowledge even when it challenges our deepest assumptions, is one of the most remarkable achievements of the human mind. We stand on a small planet in an ordinary galaxy, asking questions that reach the edge of existence itself. Even if we were never meant to discover everything, the act of trying reshapes who we are and how we see our place in the grand cosmic story. Thank you to the viewers for taking this journey, for daring to question reality, and for sharing this moment of curiosity about the universe we inhabit.